This is the Poisson distribution we're talking about now, not Poisson distribution. Probably should say Poisson or something like that, but I'm going to say Poisson. X is still the number of successes, like the binomial is. But now it's not for a certain number of trials. It's successes maybe over an interval of time, like with my basketball example, over a 2-minute period, say. Of course, I'm constrained by how fast I get the ball back. Maybe we need to imagine that when I shoot the ball, it instantaneously goes from my hand to the hoop without going through the arc in between, and it either goes in the hoop or not. And whether it goes in the hoop or not, it comes back into my hand instantaneously, and I'm able to shoot it instantaneously again. So I'm like doing it constantly, effectively. Of course, that's not real life, but if I was shooting that ball constantly and making it 40% of the time, over 2 minutes, how many am I likely to make? I don't know. 50, I don't know. I mean, if we're more realistic and we got to wait until it gets into the basket or not, and somebody's got to pick it up and pass it back to me, maybe I'm shooting once every 10 seconds over 2 minutes. That'd be like 12 attempts. So I'd make like 5 of them or so. Okay, like keep it simple. Let's pretend I average 5 successes over 2 minutes, or equivalently 2.5 successes over 1 minute. Your average could be a non-whole number, even though X itself has to be a whole number. If lambda is my average number of successes in a unit interval of time, average number of successes I spell successes right? I guess I did it twice that way. All of a sudden, I'm not sure if that's the right spelling of successes. Over a unit interval of time, I'm thinking of it as being a minute. But I could change my unit interval to being an hour, or a day, or a week, or a month, or a year. Depending on the application, use whatever's most natural for your measurement unit for time. Not of a unit interval, over a unit interval. S is the letter used to represent the number of unit intervals that you happen to be thinking about. For me, it's a 2-minute period. If my unit interval is 1 minute, and I'm shooting the baskets for 2 minutes, that would be a 2-minute time interval. S would be 2. It's the number of unit intervals. And we let K be lambda times S, which would represent the average number of successes in S unit intervals. Now, when I phrase it like this, you would typically imagine S to be 2 or 3 or 4 or 5 or something like that. But it doesn't have to be. It could be 2.5. Representing 2.5 minutes. It could be a decimal less than 1. It could be 0.5, representing half a minute, or 0.25, representing 15 seconds. Yeah, this is not the only way to think about it. This is the way I'm teaching you, the way the book thinks about it. There is a benefit to thinking about it this way, but I'm not going into those details right now. What is the probability mass function for such a random variable called a Poisson random variable? Based on various assumptions, the PMF, little f of x, which is for a discrete random variable, the same as the probability that the random variable equals little x, turns out to equal e to the negative k power times k to the x power over x factorial. What kind of assumptions need to go into this? You need to assume make some technical assumptions about the way the experiment occurs. It's called the Poisson process. I don't really want to go into those technicalities, at least not today. I'll just say this is based on assumptions of a so-called Poisson process. Kind of technical assumptions, analogous to assumptions that we've had for the other random variables, like independence and identically, just identical independent trials, kind of analogous to that, but it's different here because we don't have a fixed number of trials. In theory, capital X could take on a value arbitrarily large. In practice, if I'm shooting free throws over 2 minutes, not really, right? Because I got to wait for the ball to come back to me, and the ball when I shoot, it's in the air for a certain amount of time. So in practice, X really couldn't be arbitrarily large in that situation, even if I was 100% free throw shooter. But for the theory to match up with the practice exactly, or really well at least, the assumptions of a Poisson process need to be true or approximately true. But I will tell you, just like with other situations, people often assume, in this case, that it's a Poisson process, even if it's really not quite, for the sake of simplicity. That's what mathematical modeling is all about. You kind of hope you can get away with simple models, and then you test your models against reality. And if they don't match reality, then you're like, okay, I guess it's too simple. Insurance companies use this kind of thing all the time to, for example, count the number of hurricanes hitting Florida every year. Seriously. It's a simple model for the number of hurricanes that might hit Florida over a year. Now, how many is that? Maybe 2 on average. Maybe it's a better model if you assume the unit interval of time is a 5-year period. Maybe it's more reflecting the assumptions of the Poisson process. Again, I'm not saying what those assumptions are. So if I'm pretending that my average number of successes over 1 minute is 2.5, and I've got 2-minute time intervals, that means this is 2.5 times 2. I would imagine averaging 5 successes over a 2-minute time interval. This is my example. Free throw example. Where time is measured in minutes. So I use 5 for my value of k, and if I wanted to find out the probability that I make 4 in 2 minutes, I'd use k as 5. I'd say the probability is e to the negative 5 times 5 to the 4th power divided by 4 factorial. E to the negative 5 is, of course, a small number, but 5 to the 4th is a large number. What, 625? That's too big. That's not a probability yet. I got to divide by a large number, 24. There's my approximate probability that if on average I make 5 free throws over a 2-minute time period where I keep getting fed the ball as quick as possible, there's my probability of making 4. Calculate a program to do a Poisson? Yes. Okay, here's something tricky. The lambda right there is the k, not our lambda. That's a difference in perspective. That's slightly different than our book. The lambda used right there is our K. Yep, 0.1755. Would this probability be the same as the probability of making 2 free throws over 1 minute? If my K was 2.5 and lambda is, excuse me, not lambda, and I'm after the probability of making 2, am I going to get the same answer? Not necessarily. Maybe by luck it could happen, I'm not sure, but e to the negative 2.5 times 2.5 squared divided by 2 factorial, that's about 0.26. It's really the same kind of setup. I'm averaging 2.5 made over 1 minute. I'm averaging 5 over 2 minutes. But the probabilities, the corresponding probabilities that you might guess could be the same or at least close together, making 4 over 2 minutes versus 2 over 1 minute, are different. In a sense, intuitively, over a 2-minute time period, it's kind of like where you've got more trials to have relatively to sort of spread your probabilities over, so to speak, than over 1 minute. And that's why that probability is a bit higher intuitively. How about spreadsheet? Does it do Poisson? Equals Poisson, yep. X is the number of successes, say 4 successes. Then the mean is the K. Is it a PDF or a CDF that you're after? We're after a CDF, so I can either type a 0 or a false here. 0.1755 like we got before. If you do a 1 or a true at the end, that's a CDF value, a capital F value. And yeah, we can do it in mathematics. I'm not going to bother. I've been calling K the mean here, but is it really the mean? If that's my PMF, is the expected value equal to K? That shouldn't be very clear. But it is. I think we have time to derive that in our last 4 minutes here. First of all, it is a PMF. If I add up the values of these things, X going from 0 to infinity, X is the number of successes. It could be 0 successes. It could be arbitrarily large, in theory, at least, if not in practice. The K doesn't depend on X. That can be factored out, e to the negative K. And I hope this kind of infinite series looks familiar. Well, maybe if I write it out, it would be more familiar. If there's an E there, it's got to be related to E, right? When X is 0, it's 1. When X is 1, it's K to the first over 1 factorial. When X is 2, it's K squared over 2 factorial. Oh, our favorite series from Calc 2. That's e to the K. E to the negative K times e to the positive K is 1. What about the moment generating function? Mx of t is the expected value of e to the tx. Maybe this isn't so easy. What should I do there? Well, x factorial is the same as x times x minus 1 factorial. So I guess those x's can cancel. And maybe to make the x minus 1 there in the factorial match a power of k that would be x minus 1, that might be a good thing to do. We should write k to the x as k times k to the x minus 1. Oh, and actually, if I do this, it's a little funny. The x actually has to start at 1 now instead of 0. Can't do -1 factorial for one thing. And for another thing, if you write out the sums the long way without a summation sign, you'll see that you can start at 1. Anything that doesn't involve x can be factored out. And maybe I should do a change of variables, so to speak, let u equal x minus 1. You can change variables in summations, not just integrals. But the nice thing with summations is you don't have to find du. There's no du to find. Oh, this should be e to the k. Oh, k, e to the negative k. Oh, I made a mistake. Oh, sorry. I guess I'm finding the expected value of x here, not the moment generating function. Okay, I'm finding the expected value of x from scratch. And it is k. Okay, I could have tried finding the moment generating function. And I would have been doing this summation instead. Okay. And I'd probably, if I'm going to finish that, I'd probably want to combine those two things because they both have a power of x. Help me finish it. You should be able to do that in your derivation. I'll let you see if you can finish this. Okay.